Hi! In the previous videos we have developed a general framework describing soil processes, modeling soil processes, and this as support for soil water management and engineering. And we translated this framework and implemented this framework for describing soil water transport in unsaturated soil. The result of this process can be summarized with the 4x2 list. We have indeed two physical principles. A principle that allows to describe the flux of water in soil, which is the Darcy equation, and the principle of soil water conservation, mass conservation. When we combine both principles, we obtain an equation which allows us to describe water content as a function of time and as a function of space. The more detailed development resulted in two types of equations. The first equation, the Richards equation, is a translation of the previous principles expressed in terms of the soil suction head. It allows to describe the soil suction head as a function of time and space. The Fokker-Planck equation allows to describe the water content as a function of space and time. Both equations are mathematical synonyms. For solving these two equations, we need to parameterize the soil hydraulic functions, and there are two basic soil hydraulic functions. The soil water retention curve, which relates the water content to the suction head, and the hydraulic conductivity curve, which relates the hydraulic conductivity to the suction head or to the soil water content. From these basic soil hydraulic functions, we derived auxiliary hydraulic functions. The soil water retention capacity, which is the derivative of the retention curve, and the soil water diffusivity, which is by definition the ratio between the hydraulic conductivity and the capacity. So with all this, we generated a flow equation, which is a nonlinear differential equation allowing to describe water content as a function of space and time, and as a function of hydraulic functions, in this case the hydraulic diffusivity and the hydraulic conductivity. This is a differential equation which allows to describe a dependent variable, a variable of interest, in this case the water content, within a representative elementary volume with a size delta z, and within a very small time step with a size delta t. For practical applications, we are of course not interested how the dependent variable changes within this small volume and within this small time step. We would like to know how it changes continuously in space and time. So therefore we need to integrate this differential equation. For doing this integration, we need to define the conditions of the systems at the limit of the systems. So we need to define what is called the initial conditions, which is the limit of the system in time. And we need to define the space boundary conditions. So if we define the space boundary conditions and the time boundary conditions, the initial conditions, and if we define also the model parameters, then we can develop explicit expressions of the variable of interest as a function of space and time, and that's actually what we need as engineers. So therefore we need to integrate these equations. Now how can we do that? Well, mathematics offers us two different types of techniques for solving differential equations. We can either use analytical techniques. Analytical techniques are simple techniques. They are rigorous, they are exact, they are fast, they can be easily implemented into spreadsheets, into an Excel spreadsheet, but they have also a lot of disadvantages because these analytical techniques, which are mathematically exact, are only applicable for very simple cases, very simple systems. That means simple boundary conditions, simple soils, homogeneous soils, characterized by simple soil parametric functions, in terms of mathematical expressions of course, with simple initial conditions. So that shows of course directly that analytical solutions have limited applicability for solving these differential equations into practical applications. So therefore, there exists an alternative. The alternative are numerical solutions. Numerical solutions are much more flexible and they are applicable for much more complex systems. They can be applied for solving these differential equations for heterogeneous soils, subjected to irregular boundary conditions, and subjected to initial conditions, subjected to complex soil hydraulic parameterizations, and so on and so on. But they have also a lot of disadvantages. Numerical techniques are by definition always approximations of the solutions. So therefore they are not exact and contaminated by modeling error. Numerical solutions are also very often computer intensive. So that means that computer power can become a limited aspect in the solution and in the use of the numerical solution. So in this slide we are going to introduce you some analytical solution, and we start with a very simple case where we evaluate where we would like to obtain an analytical solution for describing steady-state infiltration in a vertical soil and vertical homogeneous soil. So the situation that we have is as follows. We have a soil, of course characterized by a soil-air interface, and at the bottom of the soil profile we have a groundwater table. And we consider that there is an infiltration flux passing through the soil, reaching the groundwater, and that this infiltration flux is actually steady state, which means that it does not vary as a function of time. And so what would you like to know is, well, what is the consequence of this flux in terms of water content within the profile? We are in steady state conditions, so that means that the water content in this soil will not change as a function of time. Also not the suction head. It will not change as a function of time. But that does not mean that it will not change as a function of depth. From a basic soil physical course, we know that if you have a soil which is in equilibrium with a groundwater table, that we will reach a kind of unsaturated system where you will have a complete saturation, of course, at level of the groundwater table, and a very dry situation at the top. And we know also that in this case, for instance, the soil water profile will be somehow limited to the shape of the soil water retention curve. While in case we have a steady state infiltration, we will also have a variable water content as variable suction head as a function of depth, but it will remain constant as a function of time. And so we would like to solve the flow equations in order to calculate the profile of the water content, the profile of the suction head as a function of space. For doing that, we need, of course, to define a reference system, and in this case we position a reference system with its origin at the interface between the groundwater table and the soil, and we suppose that this reference system is pointed upwards into and towards the unsaturated soil. With all these hypotheses, we add or we describe our equations that we would like to solve. First of all, we use in this case the H formulation of the flow equation, so we are using the Richer's equation, and we consider that we are in steady state, so that means that the fluxes, which varies as a function, which is a function of depth, that these fluxes as a function of time does not change. Means we have a constant steady state flux. Water content and the suction head, they remain constant in time. And we add additional conditions with respect to the boundary condition. We consider that the suction head at the level of the groundwater table, so where the origin of our reference system is positioned, that the suction head at this place for all time is actually constant and equals to 0. That means that we consider that the soil is completely saturated at the level where the groundwater table is present. Finally, we consider also that the hydraulic conductivity function in this case can be described with the Gardner model, which is a simple exponential model parameterized with two parameters, the saturated hydraulic conductivity Ks and the alpha parameter, which has a dimension of 1 over length, for instance 1 over centimeter. With all this, we can now try to solve the Richer's equation. We start with our mass balance equation, which actually states that the variation of water content is equal to the variation of the fluxes across the boundaries of the representative elementary value. Now in our case, this equals to 0 because we are in steady state conditions. Our water content is not varying as a function of time. We formulate also our Darcy equation, which actually states that our flux is equal to the hydraulic conductivity, in this case modeled with the Gardner model, times the hydraulic gradient. and we rewrite this equation in order to come up with an expression of z on one hand and h at the other hand. So we do that very simply. We isolate gradient of the suction head as a function of depth, and then we separate the variables from, we write at left hand side the z variables, at the right hand side the h variables, and then we have a differential equation that we actually can easily solve. Solving this equation means that we need to integrate z and that we need to integrate over h. Our integration boundaries for z starts at the level of the origin, which is situated at the interface between the soil and the groundwater table, and we integrate upwards up to a given depth, which we denote here in this expression with z star, and we integrate h from the groundwater table up to h star. Now this is of course a very simple integral to solve. This one is a little bit more complicated, but there exists also an analytical solution for this integral, and you can eventually use Python symbolic calculations in order to come up with an exact solution of this integral. Now if you do this integration, come up with this equation, and which allows us to express h as a function of z, or z as a function of h. And this functionality, this relationship, is of course driven by the boundary conditions, GW, and the hydraulic properties, Ks and alpha. So here we have a solution. It allows us to describe continuously h for each place in z, or z as a function of h. Unfortunately, this is a function which cannot be easily inverted analytically, so we can write z as a function of h, but numerically we can very easily solve h as a function of z. Now in the upcoming Python notebook, we implement these solutions and we show how the different variables will have an impact on the total solution. So I invite you to have a look to this Python notebook.